all should be very comfortable with coordinate planes. So that's section 1-1 maybe. Right, so sometimes called Cartesian plane. After Rene Descartes, right? Cartesian. He was looking outside the window, a fly was crawling on the window, and he says, oh, look, fly is moving, and I can locate the position of fly by referring to the horizontal and vertical position. Boom, coordinate system. True story. No, no, that actually happened. Oh, Isaac Newton with an apple, that's a whole other story. He came up with all that kind of almost on a dare before he turned 26. So, so coordinate plane, so you're familiar with it, right? You have a basically an intersection of two planes, two real number lines, right? And you have the origin, and then each point there has x and y coordinates, right? Called ordered pairs, so hypothetically speaking, this is 3, 2, right? Or any other point, so ordered pairs. Did you learn anything right now? No, right? Okay. So let's talk about the more important thing is looking at the distance between points. On the plane. So if I have two arbitrary points on the plane, and x2, y2, I actually want to find the exact distance, let's call it d, between these 2 points. Okay? So about to derive a distance formula. Some of you have seen it before, some of you haven't. But really it all comes down to Pythagorean theorem. We can make a little triangle, right? A 90-degree triangle, and I can figure out the length of this side, and I can figure out the length of that side. So if you know 2 sides of a right triangle, you can find the third side by the means of Pythagorean theorem, right? You with me on that? So the length of this side will be just the difference in the y values. So that's just y2 minus y1. That's the length of this side. So similarly, the length of this side would be x2 minus x1. Is the change in the x values, right? So therefore, by the Pythagorean theorem, we know that the hypotenuse squared equals the sum of squares of both legs. Right? We get that out of the Pythagorean theorem. One side squared equals the other side squared plus the other side squared. And so for d, we're just going to take the square root. So this is the distance formula. So if I give you any two random points in the plane, using that formula, we can find the distance in between, right? That's the idea. So for example, I already wrote that. So for example, if the 2 points are -1, 3, and 2, 7, I can find the distance in between. So d equals square root, and then we're just going to subtract the x values. It doesn't matter in which order you subtract them. You should still get the right answer. So what do we end up with? 3 squared plus 4 squared? Is that right? Wow. 9 plus 16, square root of 25. Kind of proud of this. It came out this pretty. Doesn't have to be. Most of the time it'll come out ugly, but that's okay. Of course I meant it. Yeah. Any questions on this? Does that make sense? Sometimes answers come out ugly. For example, if let's say you do the thing, you did a lot of work and you get distance equals, let's say, square root of 52, for example. What can you do with that? Simplify, right? How do we simplify radicals that are not perfect squares? Hmm? Yeah, right? You both kind of talking about the same thing, I think. You're trying to factor it into a product of a perfect square and something else, right? So when it's numbers like 52, sometimes it's confusing. You can do the prime factorization, right? So you see that you do have a perfect square, right? So really we think of this as square root of 4 times 13, and we can take square root of 4, gives you 2 and a 13 space, right? So we can do that, right? And we knew, right? 52, that's your deck of cards. 4 suits, 13 cards each, so 4 times 13. That's your, right? It came in handy. Questions on the distance formula? Distance formula makes kind of a little bit of sense. Again, what? Oh, good. Again, if you forget the distance formula, it's just Pythagorean theorem, where you find the length of one side, the other side, and then you use the Pythagorean theorem to do that. Okay, so the next thing we can do about 2 points is the midpoint formula, to find the midpoint in between. It does exactly what you think it's going to do. It's going to find a point halfway in between 2 other points. So again, if we have 2 points in the plane, x1, y1, and x2, y2, then the midpoint is just somewhere halfway in between those 2 points. Okay? And in order to find that midpoint, all we have to do is just to average your x coordinate and average your y coordinate. So you're taking the averages of both coordinates. And the way we do the average of 2 numbers, you add them and you half them. How's that? That's pretty straightforward. So again, for example, given any 2 points on the plane, if the question is to find the midpoint, and if, let's say, I don't know if those are the same 2 points, doesn't matter. They're really not. To find the mid, add and divide by 2. So it's -1 plus 3 over 2, and then 3 plus 7 over 2. So what do we get? 1 and 5. Right? So that point is exactly halfway in between the other two. Questions? All right. Let's talk circles. Circles are fun. We're eventually going to hopefully talk about circles at the end of this. No, we won't. So we're going to talk about circles now. So how can we define a circle? What is a circle? Yeah, but a square, 160 degrees, 300. Yeah. See, so that's what will make it a circle. So we're talking about the set of all points that are equidistant from a fixed point. Let's call it a center, and that distance we'll call it a radius. That's the official algebraic definition of a circle. That will draw a circle on a plane, on a coordinate plane. We can define it like that. So all of a sudden, distance creeps into that definition of a circle. So circle, it's really a set of all points in a plane that are equidistant from a fixed point. Called center. Okay. So we can derive an equation of a circle. So let's say we have a center, let's call it HK. So we have some point, and let's say we have a radius R. So it produces, so that point is on the circle, this point is on the circle, this point is on the circle, right? So all the points that are equidistant, if I try to connect all of them, I'll get something like that. Do you know that there's a world championship of offhand circle drawing? I'm not making this up. Takes place in Las Vegas. Yeah, there's a warm-up period. Yeah, and you just walk in and go, and they measure, and then see who wins. I'm not making this up. Yeah, so something to look forward to. I don't know. I think there's like a substantial monetary reward. I don't know about that, but I just know it exists. So anyways, so I'm not a competitive circle drawer, as you can notice. So anyways, so the way we can derive the equation for that circle, so if I just grab any point on that circle, so let's call it xy, because right now it's not a fixed point, it could be any arbitrary point on a circle. So I know the distance from hk to xy is r, right? So I can therefore use the distance formula. I can say, well, r then equals a square root of x minus h squared plus y minus k squared by the distance formula, right? And if I don't like that square root all that much, if I get rid of the square root, square both sides, I can get this. I can produce equation of a circle centered at HK with radius r, and it's just going to be this. So equation of a circle is nothing but a distance formula. And distance formula is nothing but a Pythagorean theorem. So all of a sudden we just connected circles to Pythagorean theorems, which means circles connected to right triangles. Is that fun? So anyways, it's all the same theorem, really. So now we're going to, play with that a little bit. I'm going to write down an equation, and you're going to say whether it is a circle, first of all, and if yes, tell me the center and the radius. Does it sound fair? Okay. So here's the game. Is this a circle? So I'm going to write an equation. So let's say x minus 2 squared plus y plus 1 squared equals, how about 4? It is a circle, yes. What is the center? 2, -1, that's correct. What is the radius? 2, very good. Isn't that a fun game? So first of all, it is a circle because it looks like that, right? The way I can make it not a circle, if I make this a minus right there, so all of a sudden it's getting a little weird. That won't be a circle. Yeah. If I had a minus in between there, that wouldn't be a circle. It would be a hyperbola or something else. But yeah, so you're basically looking for all pluses, and then you're just matching this with that. So what is subtracted from x? 2. What is subtracted from y? -1. So you're kind of doing the opposite sign thing, because the minuses are already in the formula. Okay, so h is 2, and k has to be -1. So yeah, so the center is 2, -1, and the radius is 2. I can graph it, right? Shouldn't be too hard to graph this circle. So where is the center? +2, -1, and the radius is 2, so it'll actually touch this. It'll be tangent to the y-axis, something like that, right? The center, 2, -1, radius is 2. Good? Okay, that's a fun game. You think you're winning? How about that? Is that a circle? Hmm? Yeah, it is a circle. What is the center? -1, 0. What is the radius? Square root of 5. It will be a lot harder for me to draw that circle because of the funky radius, right? But at least I know it's a circle. It satisfies the formula. So the center is -1, 0. Radius is square root of 5. Is that okay? How about this guy? X squared plus y squared equals 1. Is that a circle? Center, origin, radius, 1, right? So it's so-called unit circle is a circle of radius 1 centered at the origin. So the center is 0, 0, radius is 1. You enjoying yourself? All right. How about this? Is that a circle? Well, it's not obvious. Do you agree with that? Okay. What if I tell you, yes, it is a circle? And can you tell me the center of that circle? No. No. You kind of, what do you, no, 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 no. What would you do about the x's? Yeah, but I have an, oh, I'm sorry, I meant that to be an x. Yeah. Which was still a circle. It's still a circle. But how? How would you factor them? But you kind of think you do need to mess with it. Let's just agree with that. We have to mess with it. Now, okay, but I mean, what's your goal? What do you want it? So you're gonna mess with it. What do you want this thing to look like? Yeah, but there's nothing I can simplify right now, right? But I want to make it look like that, don't I? That's the goal. That's what tells me that something is a circle, and I can read all the information from it, right? What? Oh, okay. You know foiling, right? I remember I remember you foiled before. So, um, so what do we call this idea or technique that you take a variable that is a perfect square, right? Right there. That's a perfect square. And then you have that variable, same variable, not affected by a square. And you do something to it, and it turns into that. What is this? You most likely did it before, I think. What? Well, let me ask you this. If I draw this picture right here, what kind of shape is this? Can you classify that shape? It's weird, right? That's classified as weird. But what is it aspiring to be? What is it? Oh, what is it wants? Is that? Can you see what it wants to be? Kind of wants to be. What is missing? Yeah, right. Missing this, right? So if I come in and I'll do this, right? What did I just did? Yeah, I just completed the square, right? That square is a completeness. So that's what we want to do. Yeah, I know it's a long-witted. I could have just said it, but no, no, no. This is an actual very important diagram. I'll show it to you later. Who remembers how to complete the square? Because, yeah, good. Because you will see it now. You will see it when we solve quadratic equations, again. You will see it when we find vertex of parabolas. And I'm sure you'll see it some other place again. So it's kind of an important technique that pops up. And it refers back to this two, well, at least my favorite formulas. A plus B squared, what is that equal to? if you were to open it up? There's more. Well, no. Almost. What? 2ab. It's a squared plus 2ab plus b squared. Did you know that? If you're in doubt, write a plus b next to a plus b, then FOIL, you'll get a squared, ab, b squared. So you have two ab's, right? And here you get the same thing. Well, we just did mental FOIL. That's cool. That's only same thing, only with a minus. Okay? So these trinomials are called perfect squares. There's a perfect square trinomials because when you try to factor them, they become little perfect squares, right? For example, if I write like x squared minus 10x plus 25, I notice that I have a perfect square up front, perfect square in the back. And what number is being squared here? And if I double 5, so it matches this perfectly. Here's the double. So then I don't need to try very hard to factor it, because I notice a perfect square. If I don't notice a perfect square, and I use old school factoring, saying I need two numbers that multiply to positive 25 and add to negative 10. Those are negative 5 and negative 5. These are the two numbers that multiply to positive 25 and add to negative 10, right? So you get the same thing, x minus 5, x minus 5, x minus 5 squared. So that's what we're trying to fake. We're trying to fake this little number here, because I have an x squared, then I have something with an x. I need to find this number. Well, what if I just gave you that? How do you go from here to knowing that you're missing a 25? How do we come up with a 25 here? I mean, are there any hints in, I mean, the number 10 in the middle is supposed to kind of hint you to pick 25. Because if you think about it, what did 10 come from? 10 is 2 times something, right? And that's something squared. Is that what you're looking for? So if 10 is 2 times something, what is that something? 5, and 5 squared is 25. So really what we're doing, we're just taking a half of that number, and we're just going to square it, right? Take a half and square it. So the way we're going to treat this problem is take x squared. I'm going to put 6x next to it. I'm going to start grouping my variables. I'm going to leave a little gap. Then I'm going to write y squared minus 4y. I'm going to leave a little gap there. I'm going to put an equal sign, and I am going to get rid of that 3 because it's annoying. So I'm going to add 3 to both sides. So equals 10. Oops. I want to drag it here. So what I want to do now, I want to complete the square for both x and y. Okay? I want to add this magic number here, so it turns the x's into a perfect square. So remember what we agreed on? How do we find that magic number? Yeah, I'll have the 6. Yeah, x is already accounted for. And then I'm going to square it. So what am I really adding? 9. Right? 9 is the missing piece from a perfect square. So all we did, you took a number, you halved it, and you squared it. Right? Is that okay? See where 9 came from? Now, can I just walk over to an equation and add 9 to one side? I had to add to both sides. Very good. So if you add 9 to one side, you have to add 9 to the other side. Okay, so let's repeat the process for the y's. What are we going to add there? 4, right? Whoever said 4. Because you're taking a 4, and you're going to slash it in half, but then you're still going to square it. So you're adding a 4, but you're adding a 4 to both sides, right? How does that sound? Yeah, because now first three terms is a perfect square, right? If I factor them, I'll get x plus, well, what's being squared there? 3, so it's x plus 3 squared. This thing will factor into that. On the other one, it'll become y minus 2 squared equals whatever on earth that is, 23. Now, is that a circle? That is a circle, right? And you see a center, negative 3 and positive 2, and the radius is ugly. Right? So there we go. So the center is negative 3, positive 2. Radius is square root of 23. Oh, well, that's whatever that number squared, so 9 and 4. So basically, it's whatever's in the parentheses before the square. So that's a 3, that's a 2. The minus and the plus determined by that sign. Okay, so these are the signs that come from here. So if you had a minus, it's going to end up with a minus. If you had a plus, it's going to end up with a plus. Good? All right, so that's the hard version of that game, where you have to complete the square. And the thing is, like after you see it once, you can almost guess the center right away, because you're like, well, I just have to take half of that and half of that. So negative 3 and a positive 2, right? But the thing that's absolutely nowhere near to be obvious is the radius, because you really have to complete the square to find the radius. Anyways, if it made sense, good. If it didn't, that's okay, because you're probably not going to do this on the homework or something like that. But you will see us completing the square, so kind of that's me poking your complete the square button, because it will come back. Okay? All right, good. Now let's do the opposite of this game. I'll give you some information about a circle, and you're going to tell me the equation of that circle. Okay? So find equation of circle. So if I tell you the center is negative 1, 4, radius is 4. So all you have to do is to give me the equation. $16. Good, you didn't fall for it. Usually, when I give a perfect square, people tend to say it's a 2 instead of squaring it, because now you're doing everything in reverse. Right, good. Yeah, you just plug everything into the formula. X minus the x coordinate squared, y minus the y coordinate squared equals the radius squared. Fun stuff? Yeah. How about this one? I'm going to give you, so end points of the diameter. How do you spell diameter? Like that? Okay, end points of the diameter. Negative 2, 7, and what will be another good one? 6, 1. So you have a diameter of a circle, right? I'll just give you the coordinates of the end points. That's all you know. Well, you're supposed to tell me what the equation is. Very good. Because the midpoint formula will tell me what? The center of the circle, right? Because the center is on the diameter. And if you know the endpoints of the diameter, finding the midpoint will give you the center. So good. So first, we're going to use the midpoint to find the center. So in this case, it is 6, basically minus 2 over 2, right? And then 7 plus 1 over 2. It looks like what? What? 2, 4. Right. 2 and a 4. So that's the center. Now, how do we find the radius? I mean, there are two ways of doing that. You know a center, you know a point on a circle, right? You can probably use the distance formula to find that. But then remember that the equation of a circle is the distance formula. So I can just plug everything into the equation of a circle and it will just spit out the r squared part. I know that probably didn't make a whole lot of sense. Let me explain. Because look, if I look at the formula for the circle, I just found h and k, right? That's my center. Well, x and y is any point on the circle, and I have two of those, right? So I know hk, and I can take, let's say, 6, comma 1, and I can put 6 for x, 1 for y. So the only thing that's left unsolved is the r squared. So the r squared will just come out for free from this, right? Does that make sense? Because I have everything to plug in. The only thing left is r squared. So I'm just going to take 6. And I'm taking the second point because it's all positive. It's just easier on the eye. So it is 6 minus 1 squared plus, why did I say 1? I meant 2. 6 minus 2. 2 because of the center, right? And then it is 1 minus 4 squared equals r squared. Again, I know, I'm on a roll. 4 squared plus negative 3 squared equals r squared. Wow. So it's 16 plus 9, 25, and that's the r squared, right? Even if it wasn't that pretty, it will still be okay, because I'm solving for r squared. Never ask you what the radius was. So then the equation is x minus 6 squared plus y minus 1 squared equals 25. That's the equation of that circle. Because that gave us the r squared. What goes into the equation? Yeah. You're right. It would totally be 2 and a 4. But I was just making sure you're paying attention. Because, yes, the center's supposed to go in there. You're absolutely right. Good. 2, right, and a 4. Okay, yeah. Make sure it's a center. Questions on this? So I was just going 6 minus 2, right, so that's a 4 squared, and 1 minus 4. Okay. How's that? Good. Let's take a little break. I'll usually be giving you a break in the middle, unless you want to keep going. Take a little break, get some fresh air, and then... So yeah, we're talking linear equations with two variables. So, when I say linear equation with two variables or lines, what comes to mind right away? What is this concept that goes together with lines all the time? What? Intersecting could be, yeah. Slope, that's the one that's always like together. What do you know about slope? How many of you heard the word slope? Right, okay, well, tell me what you know. What? That's equation of a line. M is what in that equation? Slope, B. What is B? Y-intercept. Good. Tell me more about just the slope. Rise over run, kind of direction more, right? Okay, rise over run. Okay, good. So you know it all. Is it shaking? Is it shaking? Not anymore, but it was, right? That's it's not just me. Okay, so all right, so good. So slope, we know slope. Yes, when they do that, I'm sorry. Let me do something. Okay, so you said slope is rise over run, right? Change in y, someone said. Does anybody know a fancy math symbol for change? Yeah, so it's a capital, you're right, it's a capital delta. It's a Greek delta. So delta y, delta x. Change in y over change in x. We don't like writing a lot of things in math. We like to abbreviate, right? What? Okay. Or, if you have 2 points, here's the actual formula that we use to find the slope. So if I give you 2 points, you can find the slope of a line that goes through those 2 points using that formula, right? How many lines go through 2 points? 1, right? So slope will give us the direction of a line. So if I tell you I have a line that goes through this point right here in that direction, there's only one line that does that, right? So therefore, in order to define a unique line, I need 2 things. I need to have a slope, and I need to have a point. Having these 2 things, I can find equation of a line. So somebody said mx plus b a while back, right? So these are some equations. So y equals mx plus b. And you already knew that that's a slope. That's the y-intercept, right? And we call this slope-intercept form because slope and an intercept. There is another equation of a line. Y minus y1 equals m times x minus x1. And that one is called point slope. Very good, because it has a point and it has a slope. So if you have a point, any point on the line, and you have a slope, the easiest thing to do is to plug them all in here and simplify and make it look like that. Okay? You with me on this? So I don't know how many times you were in a classroom where somebody presented. Multiple times. Is that right? Okay. So for example, if I write something like this, y equals negative 5/7 x plus 1. Can you sketch a graph of that line? Yes. You need a slope. What is the slope? Negative 5/7. What is the y-intercept? 1. So that means we'll start at 1. And what does negative 5/7 mean? Yeah, so you're down 5. 1, 2, 3, 4, 5 over 7, right? Down 5 over 7, down 5, up 5, 7, back, right? Same thing still. Yeah, but let's just agree to go. Wow, I didn't see the other point. Because it was covered by, but yeah, so that's the idea. Does that make sense? Okay, so having that, we can sketch the line very easily. Now, finding equation of a line. So if I tell you, find equation of a line that has the following characteristics. Has a slope of 3 and goes through negative 1, 3. So we have all the necessary information to find equation of that line. I will take point slope form. I like to start with that form and then plug everything in it, right? So I can plug in the slope and I can plug in the points and then simplify. So it is y minus 3 equals 3 times x minus negative 1. Is that okay? So you're taking everything that's given and you plug it into the point slope form, and then this can be simplified because we usually like our answers in the x plus b form because that's the most friendly one. Now that's a lot of 3's. And then add 3 to both sides. Good stuff. What if I tell you find equation of line through negative 1, 3, and 2, 7? So I gave you 2 points, and I'm asking you to find equation of a line that goes through those 2 points. How would we do that? Yeah, find the slope first, and then go like we did before. So first, find the slope. So that will be 7 minus 3 over 2 minus negative 1. So it looks like 4/3. So now we're back to this problem. We'll take point slope form. We have 2 points now. I can take any one of them. Plug it into this formula. I just found the slope. So which point would you like, the first one or the second? What? 2 and 7? Okay. So you'll get y minus 7 equals 4/3 x minus 2. Right? So then simplify this a little bit. So it's 4/3 x minus 8/3. Right? And then add 7. What do we get? What is 7 minus 8/3? Hmm? Hmm? Just no. I like 13/3. What'd you have? 4 and 1/3. Yeah, same thing. So yeah, 4 and 1/3. You know, you just add a fraction. You can do that. Or subtract in this case. Right? Okay. Yeah, you can leave it. when you work on MyMathLab, just pay attention to the blueprint. They'll say mix it as a, write as a mixed number or round to like 12 decimals or whatever. So follow that. For me, I don't care. Like when we take the exams, any version of 4 and a third, unless it's 4.33, then just, I'm not going to take any points, but I'll be like generally disgusted by that. And I'm just going to be picky later on. So I don't like decimals, so fractions are better for you. Right? Fractions are good. Decimals are not good. Okay, how about, what do you know about parallel lines and perpendicular lines and their slopes? So parallel lines, same slope. So in other words, slope of one line equals the slope of another line. What about perpendicular lines and their slopes? Right, so negative reciprocals, opposite and negative, very good. So negative reciprocals, that word got away from me. So let's say m1 equals negative 1 over m2, or every time you multiply slopes of, when you multiply slopes of perpendicular lines, it's always going to come out to be negative 1. And we can prove that, but I'm not going to. I believe it will require another use of a Pythagorean theorem. Okay? So with this in mind, if I tell you find equation of a line, that passes through two, 3, and parallel to what? Do you have any? Do you have a favorite line? No favorite lines. Okay, I'm gonna make a. Sure. That's a good line. Can you picture that line? Yeah. Goes through the origin. 45-ish. Okay. What is the slope of this line, though? 1. So therefore, the slope of a parallel line is 1. How about the slope of a perpendicular line? Negative 1. Good. So let's find the parallel line first. So for the parallel line, slope equals 1. So then we'll go y minus 3 equals 1 times x minus 2. Right? So then we'll simplify it a little bit. Y minus 3 equals x minus 2. So y equals x plus 1. So there will be a line parallel to that line, and that will pass through point 2 and 3. What if I ask you for perpendicular? So in this case, slope equals negative 1, right? I mean, you take a reciprocal of 1, it's still 1, but you change the sign, it becomes negative 1. But the rest will be the same. Y minus 3 equals negative 1 times x minus 2. And then we'll what? Oh, okay. So y minus 3 equals negative x plus 2. So y equals negative x plus 5. Okay. Is that all right? Now, on Monday, when we were kind of playing with my math lab, I did a few examples of vertical lines and horizontal lines. Remember that? Vertical lines is x equals whatever x equals. Right? If I ask you, find equation of a vertical line that goes through that point, you'll just say, well, x is always 2. That's the vertical line. If I ask you, find the horizontal line that goes through that point, well, horizontal line y stays the same, so y is always 3. So y equals 3. Remember that we did that when we were answering your questions on your quiz? Yeah. So we did that because we got to talk about functions a little bit. We also mentioned the y-intercepts and the x-intercepts, how you find the x-intercepts. You said y equal to 0. You solve for x, right? Let me write that down. Just in general, for any equations. So to find the x-intercept, because every x-intercept has 0 for y-coordinate, right? If it's on the x-axis, y equals 0. So to find the x-intercept, we will set y equal to 0 and solve for x, right? Well, to find the y-intercept, it's on the y-axis, so the x-coordinate is always 0. So we'll set x equal to 0 and solve for y. Hmm? Remember when I was covering one part of the problem and then covering another? It was like a 5x and 7y equal 35. We're graphing something like that. But that's true for all equations. Okay. Another interpretation of a slope you kind of need to keep in mind that one way to interpret the slope, that slope, they're running around again. See that? Slope is rate of change. Slope tells us how fast the y value changes with respect to change in the x value. Right? It's a ratio of change in y to change in x. So if you get paid hourly, your hourly pay rate is the slope of your paycheck. Right? Whatever dollars per hour. For every hour, that's your gain. Right? Your speed, you're driving along in the speed of whatever miles per hour. That's the rate at which your velocity, with which your position changes with respect to time, right? So slope is the rate of change. We'll keep that one in mind. It might come in handy one day, and we're all glad that we realized that. Gave us like scientific revolution and such. We got that point. Okay, good. All right, let's talk functions a little bit. Now this could be new completely. How many of you dealt with functions before? All right, most of you. Yeah. Oh, no. This is probably back to 1.2, and we kind of did 1.3 and 1.4. So I'm floating in between. Yeah. I believe Monday. So you still got 5 days, and I recommend you suffer through homework at least one, because they'll prep you. And you have 2 shots at the quiz. Do you know what we're talking about? Oh, talking to Alex there. Alex, is that okay, or Alexander? Well, you got to look at the syllabus. It's all there. And you're like, well, I'm not sure what that is. And that's on Canvas. You know what that is? I don't think I have it printed. We'll talk. Actually, I do. I think I do. We'll talk. The rest of you. You know what we're talking about? Remember, you have 2 shots at the quizzes. But I believe the due date slash time for the quiz is set like Monday, 1 o'clock. Boom, and you get locked out. Yes. Best out of the 2. So, there's the only reason not to take it second time if you're out of time. You know, I'll get 100, but might as well, because if you get 100, then you probably, hey, you're getting a kick out of it. Is that cool? Yeah, Monday. So functions. So we introduce a notion of a relation, and we define relation as a set of ordered pairs. That's all it is. Set of ordered pairs. So for example, a little bit of a set notation. If I say R equals, so that's the set, and then you list the elements in the set, and then you close the set, right? How many of you dealt with set curly? Is that something we're not certain about? Let me talk. Well, okay. I'll dive back a little bit. So now we'll just list things. Ordered pairs, whatever I want. 1, 2, 2, 3, 0, 1. Okay. So here I have a relation. Set of ordered pairs. 1 relates to 2, 2 relates to 3, 0 relates to 1. For whatever reasons, I don't know. That's what I see in that definition of that specific relation. Okay, that's just a silly example. That's all I know. I don't know anything else. All I see is 1 relates to 2, and 2 relates to 3, and 0 relates to 1. If 1 relates to 2, does not mean that 2 relates to 1. That's kind of weird, but it has to be one-way street. A classical example of that, let's come up with a relation that, one number relates to another if the first number divides the second one. So 3 relates to 6, 3 relates to 9, 5 relates to 10. Does that make sense? But it's not the case the other way around. 5 does not relate to, 10 does not relate to 5, because 10 does not divide 5, right? So it's a one-way street. So these numbers right here, they form a domain of a relation, and those numbers are called the range of a relation. So domain is where you're starting, that's the domain, and where you're going is the range. So this particular relation has only 3 elements in its domain, and it has 3 elements in the range. So 1 relates to 2, 2 relates to 3, 0 relates to 1. And I'm only pointing in one direction. Doesn't work back. Right? So any kind of graph that you ever saw is a relation. Circle is a relation. Squiggly line is a relation. Line is a relation. It's a relation between x and y, right? Because again, when I look at, here's an example of a, I don't know, funky looking graph, whatever that is. It's a relation. It's a set of ordered pairs, right? It's a collection of ordered pairs. That's all I need. There are no restrictions on what kind of ordered pairs I can have, right? Now, here we're going to talk about functions. And the functions are very special kind of relations. And some of you already know what functions don't like. Functions don't like to have one input from the domain relating to different outputs in the range. So you cannot get different results for the same x value. Basically, that's what it says. Okay? So Like when I do this little graph, like right here I see, oh, look at that. I have the same x value, but it corresponds to two different y values, right? So that's not good. I don't like that. So that's not a function. So we utilize the so-called vertical line test. If I give you a graph and you put vertical lines through it, and if it only intersects at one point, you get yourself a function. Who's with me on that? Circle is not a function. I mean, take out your calculator. If you have a graphing calculator, which you don't need, but it's a challenge to graph a circle on a graphing calculator. It's going to be a challenge for me to graph a circle on any kind of graphing utility. Because look, we were playing with some of them. No, Desmos didn't work. How about full plots? Let's take one of those circles, right? I don't even, x minus 5 squared plus, I don't know, y squared equals, let's make it pretty, 4. It will, yeah, it doesn't like it, right? Because look, it says function y of x. That's not a function. Parabola, yeah. Well, if it's a sideways parabola, it won't work because it fails at the line test. The only way I can graph a circle is if I solve for y. Look, if I solve for y here, I have, yeah, I can do that. Isn't that cool? I'm writing on their website right now. That's the equation I typed in. If I solve for y, I'll get this, 4 minus x minus 5 squared, right? And then I take the square root. Now remember, when you solve equations and you take square root, you get plus or minus thing, right? So it really splits into two separate expressions. So I can graph them separately as two separate functions. The plus gives me the upper semicircle, the minus will give me the bottom semicircle. And then it will look like a circle. Because look, if I just do it like that, if I type in square root of 4 minus x minus 5 squared, hey, you see that? It's a semicircle centered at 5, 0. But I also need another one, so I'm going to type in the same thing, only with a minus. So this is how I can graph a circle, by graphing two separate functions. No, it's like different type of coordinates. Polar are fun. Yeah. But see, that's the only way I know how to graph a circle using your regular Cartesian plane. Just for the sake of geeking out, I can, know how easy it is to draw a circle in polar. Yeah, all I had to do is to type in 2, and I drew a circle of radius 2, centered at the origin. That's cute. Anyways, that's later, or ever. But do you see what makes a function a function? You cannot have one x going to two different y's. So vertical line test, all that stuff, all right? So a special function notation is this whole, basically we're replacing y in your regular equations with f of x. That's how we read that, f of x, right? And f is the name of the function. X is the independent variable. How many of you seen that notation? Okay. So for example, f f of x equals, I don't know, 2x squared minus 3x plus 1. Hey, it's a function. I mean, I can ask you to graph it, but it might be a little tricky yet. We'll graph those later. But I can ask you this. I can ask you, can you find, let's say, f of 1? So this notation tells me, well, replace x with 1. So you'll get 2 times 1 squared minus 3 times 1 plus 1. So whatever goes in a little parentheses replaces your independent variable. That's the function notation. Does that make sense? It's pretty... did I just get 0 out of that? Yeah. All right, that's cool. Wow, I'm good today. Just found which intercept? That's a x-intercept, isn't it? Right? X equals 1, y equals 0. I can ask you, how about f of 3? 3 squared, well, 2 times 3 squared, right? Minus 3 times 3 plus 1. What do we get there? I don't think so. Do we get 10? We did get 10. 10, look at that. 10. Right? Is that okay? Whatever goes in a little parenthesis replaces the variable. So if I ask you, what is f of a? Yeah, 2a squared plus 1, right? Is that fair? What if I ask you f of, how about a daisy? Can we do that one? So I'm going to need 2 daisies over there, right? Because it's a lot of switching. So that will be 2 daisies squared minus 3 daisies plus 1, right? Whatever goes in a little parenthesis replaces your independent variable, right? Let's try a different one. F of, how about a smiley? Same thing. I'm going to need 2 smileys there. So it is 2 smileys squared minus 3 smileys plus 1. Is that okay? So whatever goes in parentheses replaces your independent variable. So if I ask you f of x plus h, 2 times x plus h squared, 3 times x plus h plus 1. So x plus h is the daisy right now, right? So you don't really need to think what it means. All you know, whatever's in a little parentheses replaces the independent variable. I can probably open up the parentheses and combine like terms and do all that fun stuff, but that's the idea. Whatever's in here ends up. Good? Okay. Another important question that we need to be able to answer about functions is the domain of a function given, this definition. Okay? It's hard to find the range of a function if we don't graph it. If you graph a function, you can find a range. So for example, if I give you a graph of a function, okay, let me make up a weird one. Well, let's do another weird one. Something like this. By looking at this graph, we can see the domain and the range. Domain, all the x values, range, all the y values. Okay? So then think about which x values were used to produce this graph. Think about all the ordered pairs that are there, which is infinitely many. So what did we use on the x-axis to produce all those points? Yeah, do we include -3? Is it part of the domain? Yeah. The way we denote that is using the interval notation. Remember, the bracket is including, you will never include infinity, right? You know about brackets? Meaning including. Or there's a set notation for that that's a little funky, but you'll see it in your book, and I'm going to write it, and I'm going to tell you what that means. You'll be seeing this notation as well. It's a set notation, like I showed you earlier with the brackets, but I cannot list all numbers that are to the right of -3. They're in the many of them. So what I'm saying is that I have a set that's full of x's, it's full of elements. The vertical bar, we read it as such that. That's how we read that symbol. So it's full of x's such that each x is greater than or equal to -3. So that covers everything from -3 to infinity, including -3. So this is just a fancy notation. Okay, so really the important part is here. Well, you will, like, especially in my math lab, it will tell you, hey, use the interval notation, or use the set notation, or there'll be like multiple choice most likely. Yeah, yeah, so that's the interval. This is the interval notation, that's the set notation. Yeah. So that's the domain. What about the range? So range, you're looking at the y values. So now we're looking at all the y values from 0 to infinity, right? There's nothing below 0, so it is including 0 to infinity. Is that okay? Yeah, it's the same set notation. And here's the funky part. I don't have to say it's full of y's, so each y is greater than or equal to 0. I can still use x. I can say it's full of b's, so that each b is greater than or equal to 0. Because set is just, it contains numerical values. So this variable is only in relation to the set itself and nothing to what it actually represents. So it doesn't have to be x for the main and y for the range when using set notation. And of course, it would be much less confusing if I just used the y. I just put it like that, and then it's just very consistent. But we don't have to, because they're representing two different variables. Okay, is that okay? So we can read it from the graph. Then you can always read, if I tell you, hey, here is a point on this graph, and it is 1, 2, for example. And the name of this function, let's say, is g. So this is the graph, y equals g of x. So I can ask you, what do you think g of -3 equals to? Can you tell me? What do you think g of -3 equals to? 0. Because you're looking for the y value, really, right? So you say, okay, x is -3. What's the y value? 0. At the same time, I can ask you, what is g of 1? And you will say 2. Because the function value is the y value on the graph. Is that okay? Okay. So far, we can, given the graph, we can find range and domain. But without a graph, we can only find the domain. We cannot find the range yet, at least, if we don't see the graph. So domain of a function. You have to look out for two trouble areas right now, and we kind of talked about it Monday again. It's the division by 0. That's a big no-no. And it's taking square roots of negative numbers. That's another no-no. For the domain, we want the function to produce real answers. Okay? Division by 0 is not real, and square roots of negatives is something else. It's not real. Okay? So look for those two areas. So trouble areas for now. Division and even radicals. So for example, all I'm asking to find the domain, and let's say here's a function, and we'll take our favorite function right now. What is the domain of that function? All real numbers, right? There are no trouble areas. There's no division. There's no possibility of dividing by zero. There are no square roots or anything like that. So all real numbers, right? That's a lot to write. All real numbers, right? So there are two things I can do. I can use the interval notation from negative infinity to infinity, right? Or there's a very fancy set notation for all real numbers. There's a little letter that just represents set of all real numbers. You know that? You know a fancy symbol for the set of all real numbers? Yeah, like a weird R, right? It's like a double-legged, like a fancy-looking R. Set of real numbers. And I'll tell you more about this on Monday. I'll give you the dissection of sets, and because they're like natural numbers and real numbers and rational numbers and irrational numbers, all that fun stuff. But for now, we can just use this. Okay, how about f of x equals x plus 1 over x minus 1? Not all real numbers, so, but most of them, right? What real numbers that I'm probably not allowed to use right now? 0 and 1, right? These are the two. So I really like the set notation on this one, because I can just say it's all x's such that x is not equal 0 or 1. That's the notation, right? Interval notation is going to be pretty funky, because I have an interval notation, interval from negative infinity to 0, but not including 0, and then from 0 to 1, not including 1, and then from 1 to infinity, right? I have three intervals, negative infinity to 0, 0 to 1, 1 to infinity, and I need to glue them together somehow, and Brooke kind of whispered that already, right? What glues the intervals together? Union. And we still haven't really talked about the union, but that's it's equivalent to the addition of sets. So it means take this one together with that one. That's the union. And I'll tell you what a union is in the middle, in a minute. Okay. But the message here is make sure your denominator is not 0, right? Here's another example. Function square root of 2x minus 1. Okay. I don't have division, but I do have a square root, so I have to make sure that radicand stays non-negative, which means either positive or 0. I can take square root of 0. So I have to make sure that the radicand stays non-negative. The way we do that, you literally pick up the radicand, 2x minus 1, and you set it to greater than or equal to 0. Solve this inequality. It will tell you the domain. How do you solve this type of inequality? Yeah, treat just like an equal sign, except for a few little exceptions. When do you have to be a little careful? What? If you flip a sign, if you divide or multiply by a negative. Or if you take reciprocals of both sides, but which you never do. But that's another situation where the inequality flips. So that's really the domain. It's all x's greater than 1/2. So every number from 1/2 and on will guarantee you do not get a negative under the square root. as the interval notation. When you multiply, divide by negatives. Okay, so again, on your homework or on your quiz, when you see just a normal-looking function, the question is what's the domain? It's all real numbers. But when you see division or square roots, that's where you have to be careful. Okay? Now, really quickly about the set stuff, since it's kind of a refresher. So quick definition, set is a collection of stuff. That's all it is. It's just a collection. And the thing about the sets, they're repetition free, meaning if something is in the set, you don't need another one of the same thing in the set. So if chair is in the set, you're done with chairs. Okay, just one at a time. And it's unordered because sometimes you cannot put things in order. So the order in which you list things, unordered, is that right? Unordered. Is that a word? Yeah, is that right? I spelled it wrong. Something's wrong. And there's another ED. All right. Okay, that looked weird. Order, and then, there we go. Unordered. Yeah. So, for example, have a set 1, 2, 3, 5. So here's the notation. Set A consists of those 4 elements because I just made it up. All right? Not really. Just we kind of like to use capital letters. That's about all. Could have been anything else. We say that 1 is an element of A. We say that 2 is an element of A. We say that 0 is not an element of A. Right? Do you agree with that? 0 is not on the list. Now, we don't like writing 1 is an element of A. That's a lot to write. It seems to be we need a symbol, and we do. And here's a symbol. That weird-looking thingy stands for belongs to or element of. So that's a weird-looking C with a tongue. It's a belongs to. Set stuff, yeah. And if it does not belong to, we write it like that. So it does not belong to. Okay, so that's just a little bit of a set notation. Now that union business, the way you saw earlier. So definition, let A and B be sets. So A and B are sets. We define the union of an A and B denoted by this notation. This is a special union sign. So we define the union of A and B as a set of all elements that are in A or in B. Yeah, we already passed the time, I think. But anyways, the key word here is or. Or means it's here or there. True story. Last weekend we had like a kids party at home and we were making pizzas. And so we had the dough and all the ingredients. And somebody asked me whether I made the dough or I bought the dough. And I said yes. Because I understand the meaning of the word or. The guy got a little bit annoyed by that answer, but yeah, I was right. Okay. You know, well, I did one or the other. He's like, did you buy it or you made it? I was like, yeah. Yeah, I did one of those. That's the meaning of or.